Started, Philip?
Yeah.
Okay. So welcome to the 7th talk in the inaugural webinar series by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees and their families and their colleagues are safe amid the ongoing COVID-19 pandemic. Today's webinar will be presented by Professor Philippe Llewellyn from the Aix-Marseille University and Total from France. My name is Arvind Rajendran. I'm a professor at the University of Alberta. Together with Nick Wilkins, a graduate student here, we will moderate this webinar. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or the moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you're not already one. Our dues are very minimal at just $20 a year, but we support the publication of our flagship journal, Adsorption, and also contribute to travel grants and workshop seed funding for IAS members and affiliated groups. We also organize the Fundamentals of Adsorption, a conference that happens once in 3 years. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database from Springer. Do follow us on our social media channels, both on Twitter and on the IAS YouTube channel. We are posting all the webinars up there, and it is all free. I'm now pleased to introduce today's speaker, Philippe Llewellyn. He's a professor at the Aix-Marseille University in France. He did his PhD with Ken Singh in Roquerolle, a joint program between the UK and France, and also went on to do a postdoc with Unger and Schut in Germany. He joined CNRS in 1993, and since 2010, he is a research director at the Madurell lab there. Currently, he's spending 3 years on a secondment with Total, working mostly on CO2 capture. Professor Llewellyn has a wide range of research interests, most of them centered around porous materials. He was also the recipient of the AFCAT Cetram Young Researcher Award back in 2000. And he's also the co-author of a very well-known textbook on adsorption by powders and porous solids. With this introduction, I'll pass on the screen to Professor Llewellyn.
Okay. Let's see if this works. And then here. So, hello everybody. I hope everything is okay with everybody around the world. It's a privilege to discuss this topic with you today. So metal organic frameworks for separation and storage. I mostly talk about gases. So I'd like to thank the IAS, Daniel, Arvind, and everybody who's organizing this webinar series, which so far has gone very well. So as Arvind said, I'm a research director with the CNRS, and my research group is in Marseille, which is south of France. And I'm spending most of my time at the moment with Total, and I've been there for about a year now, working on a whole series of topics, but mostly on CO2 capture. So the plan today is in 3 stages: a brief introduction, a naive introduction into metal organic frameworks, what they are. Hopefully at the end you'll understand that they're porous coordination polymers, and that there are a whole family of materials that can be kept under the big umbrella of MOFs. I'd like you to have an idea of how they differentiate from traditional adsorbents, and maybe get an idea of pros and cons. The second part of the talk will be about the potential of MOFs for storage and separation, and for this I'll use 1 or 2 studies from the laboratory scale. We'll learn that what we can do, or what are the effects of. We'll hear about metal nodes, organic linkers, and what are the effects of these on adsorption, as well as their functionalization, especially of the organic linkers. We'll also touch on flexibility of these materials, because that is one of the things that are of interest. We'll then take a break, and then the last part of the talk, I'll highlight some applications of MOFs and some commercial openings before we go into a summary. So, some quick background. MOFs are a subcategory of coordination polymers. MOFs are porous, and the name MOF, metal organic framework, was coined by Professor Yagi. Maybe the first possible MOFs were prepared, so these porous materials prepared in the 1950s, and we can date back to this publication here. But the recent interest in MOFs dates from the 1990s, and some of the initial drivers in the field we can see here: Professor Yagi, Professor Kitagawa, and the late Professor Ferry. So from the United States, from Japan, and from France. So what is a metal organic framework? Well, metal organic framework is built up from metal nodes. Let's see if I can get to a later pointer here. Okay, from metal nodes here, and mostly rigid organic linkers. We can use a whole series of synthesis conditions to make a 3D porous and crystalline material. And in this example here, you have an example of something that's called MOF5, first prepared by Professor Yagi, also known as IR-MOF1. So as I'll show you in the next slides, we can vary these metal nodes. We can vary these linkers. We can functionalize, well, maybe functionalize these metal nodes, but it's quite easy to functionalize these linkers here. And if we have a porous space here, we can include species inside, or occlude species inside, which could be used, for example, in catalysis. I won't be talking about occluded materials species today. So just to give you a few examples of the ligand and mode variation. So this is our famous MOF5 here, which is up here in this IMOF series. And we can see that we can vary the length of these linkers, the amount of, for example, benzene rings you can see here, the phenol rings here. And we can see, initially you can see that there's a function here. But these metal nodes don't have to be these single sites here. We can have chains or other more complex nodes themselves. So within the pore space, we can functionalize these linkers. And of course, these linkers can, as we've seen on the other side, we can have linkers of varying length, but also varying means of attachment. So what are the elements that we can find in metal organic frameworks? Well, basically, here's the periodic table. And most of the elements here have been found in one type of metal organic framework or another. So in terms of metal nodes, everything that's around here in the periodic table. Within the linkers, everything that we can see up here on the top right-hand side. And of course, if we occlude species, then again, oxides or fluoride species can be occluded inside, as well as things like lithium, sodium, and other cationic species. So the range of chemistry is very, very huge. We've just seen beforehand that the range of pore size and even pore shape is also quite large. So there are a wide variety of and a spectrum of chemistries, which makes MOFs different from maybe other porous solids that we look at. We have chiral MOFs, we have phosphonate MOFs, we have sulfonate MOFs. There are even peptide-based MOFs or biomOFs as well. Another class of materials that we can put into the same umbrella as MOFs are called ZIFs, so zeolitic imidazole frameworks. And so we have a few examples here. And even though there are no real metal sites in here, there are also the subspecies or family of covalent organic frameworks or COFs. So all of these materials have come into light since the initial work of Yagi and others. So the first thing that makes things different is the variety of chemistry, pore sizes, and shapes. The second thing is that quite often MOFs are flexible. So there are different forms of flexibility. For example, the ligands here, so this is ZIF8, the ligands here can turn around themselves. There are MOFs here, for example. So this is a MOF that is flexible and can breathe. So we call this a breathing effect, and going from a closed form to an open form. And then there's ligand deformation, and I'm sure Stefan Casco is going to talk about this next week when he talks about, again, he's going to talk about MOFs but more specifically on the flexibility. So this leads us to the question, and it is a problem for those working in research, and especially in adsorption, is there seem to be too many MOFs to choose from. So just to remind you, we have this variation of metal cluster, this variation of organic linker, to give us a 3D porous network. So again, this is not something I want to delve much more into today, but we can see that there are a possibility of hundreds of thousands of different materials, whether they've been made already or whether they're hypothetical. And the one question is how to choose the best one for a given application. And Arvind is going to talk about this next week as well. But if we can vary this pore space, which we can see here in sort of green, the metal nodes that we can see here and the organic linkers here, if we can vary these from a hypothetical point of view, we can maybe choose the best ones to make and shape. So these are shaped in beads for a whole series of different applications. So this is what is shown here in the diagram, which I've taken from this publication from Seda Keskin, in which we can take a series of materials. We can fine tune them down, do some molecular simulation, have some structural performance relationships before starting experiments and working out what could be the best materials for our application. So MOFs aren't great. There are many drawbacks. And I'm going to talk about three here. The first is the problem of interpenetration. So again, this is our famous MOF 5. And we can see that if we make it, so this is a specific form of MOF 5. So we make it under these conditions with the solvent known as DEF, we can have this quite nice material. But if we make it in the DMF, for example, we can see here that we've got two interpenetrated structures, which can lead to variations in pore size and other problems. Now, the things that have been seen is that some of these MOFs, the activation or the liberation of the porosity is not always easy, and sometimes they could be organic species or inorganic species that stay inside. And this again can cause problems in some materials. So that even though the synthesis seems often, or at least from an outside point of view, fairly simple, the activation and to make sure that everything is pure and works well is quite a challenge. The second thing we have to worry about is because we have such a wide spectrum of materials in terms of chemistries, in terms of linkers, et cetera, we have also an equally wide range of properties. And of course, many materials will be stable and others maybe not. So one of the things that was seen quite initially, some of these initial materials, and here we have MOF 5 down here, are actually not so stable to steam, for example, or to temperature. And so one of the things that we have to be careful about is the stability of these materials. So this work back in 2009 showed that the people showed that they could carry out steam testing, so taking the materials, synthesizing them, treating them under steam for a certain amount of time at different temperatures. And they've compared this to the percentage of steam, and this has been compared with molecular modeling to get an idea of the stability of the materials. So we can see how down here that maybe some MOFs are not so stable, but there are other MOFs, and we'll maybe talk about CIF8 later, which are quite stable. The other thing we can sort of worry about is costs. So some of these organic linkers can be quite expensive. Some of the metal nodes also, especially if you go into some of the more that's fancy, if you like, metals and metal centers. So this can be a problem. It should not be a problem for research, but it could be a problem if we're going towards application. So for those working in adsorption, many of us know a whole series of different porous materials, from the standard activated carbons up to zeolites. We also know about silica gels, more recently periodic mesoporous silicas, templated carbons, with different ranges of order. And also we can maybe class these in terms of pore size. So zeolites are mostly microporous, MOFs microporous and move into the mesopore range. And some of these other materials are mostly mesoporous. So what actually makes MOF different from some of these other standard materials is basically what I've said, the variety of chemistry and the structural flexibility. So the next question we can ask is, in terms of research, which gases or vapors should we study, could we study, and why? So maybe the first place to start is the NIST data set, which is hosted by the NIST. You can see the link here. And what we've done, or what Paul has done, is look at the temperature of various experiments and the different gases and vapors that have been studied. So we can see that hydrogen has been studied both at low temperature and at room temperature quite a lot. Nitrogen and CO2, as well as methane and some other hydrocarbons. So these are the examples that I'm going to go through in the next few slides. Note that we can see, for example, CO2 has been studied around around 200 Kelvin, and also argon and nitrogen at quite low temperature, so it's around 77 or 80 Kelvin. And I'm guessing that Matthias is going to talk about this tomorrow. So let's start with hydrogen. Why do research on hydrogen? Well, it's a clean fuel. Burn hydrogen, you get water. Very versatile energy vector, and will probably be central if we move to a low carbon society. And these are the sort of things that the International Energy Agency suggests. If you look to their reports, they say that there have been several false starts, but maybe now is the time to go back and really look at a hydrogen economy. We can see here on the right-hand side that global demand for pure hydrogen is ever rising. So this moves into, or this points us in the direction that hydrogen storage and uses of hydrogen. So even if the uses of hydrogen will increase, so maybe the storage of hydrogen will be something that we should look at. From a research point of view, it's not an easy molecule to study. If we're carrying out experiments, we have to take care of contaminants, whether these be in the solids themselves or in the adsorption apparatus. And so one way forward is to, for example, compare the adsorption of hydrogen with that of deuterium. And so a few people do this. So if we look at results in the literature, we also have to be careful of the results and have a keen eye to see whether there are things that could be due to contamination rather than pure research results. We all know that we will be working with dihydrogen, and that the boiling point, triple point, and critical point are all below 35 Kelvin. So whatever studies we do from 77 Kelvin onwards, we are supercritical, which makes things not so easy. What we can see here is the electron density around a dihydrogen molecule. So we can see that there is a slight polar effect, and this may affect some of the results that we see. So coming back to our MOF5 sample. So again, just to remind you the structure up here. These are the sort of results that we will see for the adsorption of hydrogen at MOF5 at different temperatures. So these we see here, the temperatures are from around room temperature down to around minus 75 degrees Celsius, up to quite high pressure. And what the authors have done here is compare the uptake on this MOF5 with respect to this straight line here. And this line here gives us an idea of the volumetric density of just the compressed gas at 25 degrees C. So we can see that there is more hydrogen taken up in the material as we go down in temperature. It's logical. And we get an excess with respect to just the compressed gas. We could then wonder, what are the adsorption mechanisms? And what we see here down here on the left-hand side. And this is the direct observation of hydrogen in MOF5, and we can see that these red points here and these green points here sort of show that hydrogen would like to migrate towards these metal centers here. We can see the metal centers here in this MOF5. So we can see that a fair bit of the pore space has much less density than close to the metal side. So this gives us a first idea of how we could improve, or how we could improve the adsorption in these materials, or at least improve the materials for the adsorption of hydrogen. Just to make the point again, so we can see on the right-hand side, these authors have looked at materials that have been initially prepared under vacuum, and we get quite nice high uptakes of hydrogen here. And they compared this with a material that was left aged a little bit just in air, and we can see that there's quite a large decrease in capacity. So this is just again to make the point that some materials aren't so stable. We have to be careful of storage and stability in some cases. So what is the way forward to increase uptake? So as we saw in the slide earlier, the hydrogen likes to sit where possible quite close to the metal nodes or the metal centers. And there are a series of materials which have quite a high density of these metal centers, or coordinated unsaturated sites. So this material here is known as MOF CPO27 or MOF 74, or this lovely name here. That's a problem with naming sometimes. And this work shows, and so we have here the adsorption of hydrogen as a function of pressure. So this is in a log scale here, and we can see the uptake in 2 steps. And this first step here is due to the adsorption close to these metal centers here. You can see here. What is possible to then do is to calculate the heats of adsorption, or the energies of adsorption. So here we have the energies of adsorption in kilojoules per mole as a function of uptake. And we can see here that for this MOF made with different nodes, so with magnesium, cobalt, and nickel, we get slightly different hydrogen adsorption energies. More recently, so the group of Jeff Long has looked at a very similar material to this one, again with different metal centers, and they showed that the adsorption enthalpy was even higher. So they suggest between 15 and 20 kilojoules per mole, so slightly higher than these ones. So this may be a way forward in making materials for hydrogen storage. So what we have to do is then take a step back and look where these MOF adsorbents fit with respect to other ways, other means to store hydrogen. So of course we can have physical base, so we can compress, have liquid hydrogen or cryocompression, and compare with materials based. And what we see here from this diagram is that, or at least from this work, a lot of the studies have taken into account work that's been carried out at 77 Kelvin. And even if we do have a medium to high uptake for some materials, for example, Nu100, which has this structure here, we can see that there's a lot of engineering in terms of materials to get towards a DOE target for if we want to look for storage of hydrogen. I'm guessing for use in cars, for example. So now let's turn to methane. So why study methane? Well, methane emissions are the second largest cause of global warming. A lot of methane comes from natural sources, for example, wetlands. But there are some sources that we know of methane, for example, in fossil fuels, from waste, biofuels, and biomass burning. The difference, for example, in terms of global warming of methane with respect to CO2 is that methane has a commercial value. It's used as a fuel. It can also be used as a chemical feedstock, for example. So steam methane reforming gives us hydrogen as a starting molecule. The other thing, so even if we do have methane under pressure, what is interesting is in terms of specific energy, so energy per gravimetric density, methane is down here under pressure, has a lower specific energy than hydrogen, and quite a similar volumetric density or energy density with respect to hydrogen. So methane could be used as an energy vector to give us hydrogen. That could be one way forward. But to increase this volumetric density, one way forward is to liquefy the methane. So we'd have to go down in temperature. And of course, we know that if we carry out adsorption, one of the things that we know, or one of the hypotheses is that the adsorption mechanism is like a liquefaction mechanism inside pores. So one way forward is to carry out adsorption and maybe store methane in an adsorbed species. So just to show you, so from this review, two results with two different materials. So this is a copper BTC or HCUST1, which has 3 different types of cages. And we can see here the methane isotherms at different temperatures. And on the right-hand side, we have the similar thing for materials known as NU111. And again, we can see these isotherms, so they're here, the uptake as a function of pressure. They're quite gradual isotherms, also known as Langmuir isotherms. And we can see that there's no specific features in these isotherms, as we've seen for hydrogen so far. Again, if we want to try and localize the methane, so this has been done again for MOF5. So what is interesting in this study is we have the total uptake here in green. And what the authors have done have tried to isolate where the methane would be with respect to the metal centers here. So this is one site here, a second site here, called C1 and C2, and we can see that this. And then what they've done is they've drawn the individual isotherms for the methane placed in this C1 and then this C2 site, and we can see that they overlap here. What the authors also show is that there's a C3 site which is close to the linker here. And this is the least preferred of the three sites. So again, the metal nodes seem to play quite an important effect in methane adsorption. Again, this is taken up in a previous study where the authors looked at a whole series of different materials. And so this is just the result for a material called PCN11. And we can see here the adsorption of methane in this site here, or close to the metal centers there, or even here. And what is interesting here is the conclusions are that the methane takes place in two different areas via some types of interactions with the metal centers, but also if the cages are quite small, if they're side pockets, for example, within these small cages and channels. What was also interesting from this work is that the surface area or, for example, the linker functionality, we'll come to linkers later, are less important parameters to consider. So I've talked about the metal center and the role of the metal center on the adsorption of methane and hydrogen. Let's now have a very quick look at the effect of what the ligand functionalization could have. And I've taken here the example of CO2 and the material known as UIO66. So UIO66 here. So the structure of UIO66 looks a bit like this. So here the metal nodes are here, and the organic linkers are sort of crossing here. This is another view from different authors. So in this study, the authors carried out a screening using molecular modeling. You can see here the linker with different side groups. So here's bromine, NH2, NO2, CF3. Hydroxyl OH, SO2H, and carboxylate group here. And they carried out a screening and looked at the interaction, so via the enthalpy of adsorption for CO2 and methane here. And we can see that both actually change with respect to the different linkers. What they then did is validate some of these data with direct calorimetry experiments, which we carried out in Marseille. Similar types of results have been obtained in second study, and again these are, so we have the isotherms for CO2 here, and then the enthalpies of adsorption as a function of loading for methane here and CO2 here. We can also see that there are variations depending on the various linkers that they've put into the material. So to cut a long story short, what we see here is that the linkers have both an effect on the chemistry. We can see here for the CO2, we can see here for the CO2, different interactions, but also on the pore size and maybe the accessibility of some of these pores to these probe molecules. So the effect of ligand functionalization is not as simple as one could expect. So moving outside a little bit, the idea of metal nodes and linkers and ligand functionalization, very quickly looking at the problem or the advantage of maybe having a flexible material could have. So in this work by Jeff Long's group, we can see that they've been looking at methane in the material, which is highly flexible. So we can see here that initially the material almost has no porosity at all. And as they increase the pressure, the structure opens. And the isotherms look like this. So just as a comparison, these blue dots here are for a rigid or fairly rigid structure known as copper BTC H-cust1. And this is in green, the isotherm they obtained with this material. So initially, no adsorption of methane in the material until about 15 bar. And then this pore opening, so going from here to here, into the open pore structure. And on desorption, they see a hysteresis. So the interest of this is that if we look at methane storage, for example, for cars, for example, we're looking at a working capacity between a lower pressure and a higher working pressure. So for example, we can look at around 6 bar and around 30 bar, and we can see that this is the working capacity for this material here, and almost double the working capacity for a flexible material. And almost all the working capacity is used in the material, whereas we lose this part here for the H-cust1. So this flexibility gives us maybe an advantage in terms of working capacity. The added thing is when we look at the energies of adsorption here. So these are the energies of adsorption for methane on this material as a function. So the energies here, or the enthalpies here, as a function of methane adsorbed here. The initial adsorption is carried out at around about 13 kilojoules per mole. But as we go through this pore opening, we can see a decrease in the energy here before a re-increase as we get to higher loadings. So what this suggests is we're going from this form to this form. There's a certain amount of energy needed to reopen the pores. And this compensates the exothermic adsorption of our methane. And so the authors talk about an intrinsic heat management. So what they show here, or what they suggest here, is we get higher working capacities, but also lower adsorption energies, for example, with copper BTC and this material. And this may help in terms of processes. So going forward. So the third main topic I want to talk about in terms of research is propane and propene or propylene in terms of separation. So again, why look at this in terms of research? Well, the uses of propylene are to make polypropylene. So about 2/3 of the propane used around the world is to make this. But it's also a starting molecule for many other different compounds. The market value is huge in terms of around 100, and will move up to about over 120 million metric tons per year. So it's a huge market. From an industrial point of view, quite often propane and propene are made or prepared in almost an equimolar mixture, which means the fact that they're very close in terms of their properties makes this separation very complex and quite energy-full. So just to give you an idea, then I've taken this from the publication here. We have propane, propylene, many other different molecules here, coming in at 23 bar and at around a little bit below room temperature. And then we have a distillation, and in this setup, which is an industrial setup, is with two large columns, two very high columns. It's too high to actually have one big column. And each of these have different stages. So here, around 120 stages for each column. The product comes out at over 99% purity. And the cost of this separation is around $40 per ton of propylene. Which, if you come back to this market size in terms of millions of metric tons per year, it is a huge amount of money used for the separation. Now, in terms of research, Farouk and his group in Singapore have suggested the use of, for example, a 4A zeolite with a vacuum pressure swing adsorption system with 7 steps here. And they suggest that the costing are almost half of what we see in this industrial zone. So this means that we could have potentially, if we move to an adsorption separation with respect to this distillation, of around $2 billion which you can imagine what that would be in terms of energy savings as well. So 2 examples. The first is with this material called ELM12. Again, has a pore size around 4 angstroms, a little bit like our zeolite 4A. Interestingly, here is that what is suggested that the system has a zigzag type channel, which is shown here, highlighted here. And in terms of breakthrough, so in this publication here, in this breakthrough, we can see that what breaks through first quite easily is propane, and then breaks through quite in the second step, propylene. And it's a kinetic separation. If we go back and look at the isotherms for propene and for propene, they're fairly similar. So if we, from an equilibrium point of view, if we carried out a simple calculation using ideal adsorption solution theory, we would have quite a low selectivity number, whereas in terms of kinetics, we have quite a nice selectivity. The other thing interesting here, the enthalpies of adsorption are also quite similar. So from a thermodynamic or an equilibrium perspective, propane-propane separations would not be possible, and we'd have to go towards kinetic separations. The same type of idea is shown here. So this is work which Jürgen Caro worked on, taking this material here, known as ZIF-8. And as I alluded to right at the very start, some materials are quite flexible. And this material, we can see here, the linker can spin around on itself. And so what these people have done is that they've made a membrane. And in making this membrane, they used an in-situ electric field to make the membrane. And what they say is that the membrane is made and is actually fixed in a smaller pore system. So instead of having a system which is able to flex, what they've tried to do is distort the lattice to make it a little bit smaller. And the idea is given here. With a normal ZIF-8 material, there'd be very, very little separation power. But if they can stiffen the membrane, which is what stiffen the material inside the membrane, then maybe they can get very good separation properties. And this is what we're going to see on the right-hand side. So this is a membrane. We can see here the permeance, for example, of the propene and the propane, and we can see the difference here, which is quite large. And the separation factor is also here in blue. It's also quite nice. And what they've then done is compared with the performance with other types of membrane materials, and they suggested this work is quite good. So here we go. So before we take a break, I just want to make a first series of conclusions. If we try and understand adsorption in MOFs, and we try and make some very first generalizations, the effect on metal nodes on hydrogen and methane sort of gives us an idea that these are maybe areas of preferential localization, but maybe limited effect on the interaction strength. And we can see here, this is again the result of that we saw earlier on the CPO27 material, and for hydrogen, and the differences in energies are only around 2 to 3 kilojoules per mole, which isn't huge. What I didn't show you is here some of our work that we carried out, in which we've taken the initial enthalpy of adsorption, so what we'd measure around here, for a series of materials with different metal, made with different metals. So a similar type of material is this one. And we can see here, what I've done here is plotted for different gases, the polarizability. So going from hydrogen down here up to methane on the right-hand side. And we can see that the initial enthalpy of adsorption for the adsorption of methane, when we change or when we vary the metal centers, doesn't change too much. And I've drawn a straight line between the methane and the nitrogen. But what is interesting, for example, with the carbon monoxide and for the nitrogen, is that we move away from this straight line, which means that there is a preferential interaction of for example, carbon monoxide with its dipole with the metal center. Talked a little bit about the Lincoln functionalization, and the effects aren't as simple as we could imagine in terms of pore size and pore chemistry. And then just remember the MOF flexibility can play a role. We could have something that we want to be flexible, or something that we want to be a little bit stiff, and we want to try and limit this flexibility. So allowing or restricting or playing on this flexibility could improve potential performance. However, I'd like to, before moving on and to the next part of the talk, we have to note that most of the research is carried out with single gases or clean gas mixtures, and so not under, or very rarely under, real conditions. And that is a significant step before we move on towards applications. So with that, I'd like to stop, and I don't know whether there are any questions. So this is just to say that there are quite a lot of surprises in terms of research on these materials, not only in a material sense, but also in terms of results. So I don't know whether there are any questions at this point, Daniel or Nicola.
Yep. So there are a couple of questions on YouTube. So this is also an opportunity to have colleagues participating through the Zoom to post some questions as well. So the first one comes from Marcus Mello. Can you comment on the commercial availability of MOFs for methane storage? Are there any industrial scale commercialization at this point?
I'll come on to that in the next part of the talk, but as far as I know, I have not seen any commercial use of methane, real commercial use. There have been trials, and I don't know where BASF are in terms of methane storage or hydrogen storage for cars. I've not seen anything specific, but in terms of large-scale methane storage, I've not seen anything yet. It doesn't mean that there aren't things in the pipeline.
The next question also comes from YouTube from Alex James. Does the costing you mentioned for the C3 separation, does it just consider the cost of the process alone, or does it also take into account the cost of production of the material as well?
Okay, so
I think he's referring to Farouk's paper, most likely. Yeah.
So Farouk's material, I'm guessing it's he's done a full system costing with his material and his process. So he was the one that did a full costing of just the separation, so the cryodistillation or the distillation, which was around $40, and then he did the same rigorous costing for his system.
Yep.
So it's a full costing analysis.
So the next question comes from Guoping Hu here from Zoom. So when you talk about the pore opening MOFs for gas separation or for capture, are the kinetics fast enough to be implemented in PSA, VPSA cycles?
Good question. Depends on the system. Depends on the molecule. We heard from Stefano that the larger the molecule, the faster or the slower the diffusion. I'm not sure whether we will see this for some of the smaller molecules, for example, CO2 and methane, for something like a PSA system. But if we are moving on to larger molecules, larger hydrocarbon separations, olefin paraffin, for example, or linear and branched, then I think maybe these kinetic effects will start to see quite nicely.
Okay, I have one question myself. When you're looking at these breathing MOFs, they also tend to be very dependent on the gas environment that they are in. So what could be a potential way to rationalize that?
So I don't know whether I'm going to answer the question properly. A lot of the results that we see have been carried out with single gases. And as we go to mixtures, what could happen is that if we have the pore opening due to one gas, then the second gas will also come in. So as we try to rationalize this towards, if we want to use these for separations, for examples, we are going to need to do mixture experiments. If we then want to rationalize just the results themselves for different gases at different temperatures, then one way forward is to look at different metals, different metal nodes, and the way forward to rationalize this is in terms, or could be in terms of the metal oxygen carbon, for example, linker strength. But the way to rationalize this is initially to really look at the chemistry of these materials. But yes, temperature has a huge effect, and as we move towards mixtures, then some mixtures will not separate as good as they would with a rigid material, for example.
Excellent. I just have one comment from YouTube and one question, after which we'll move on. So the comment comes from David Madden, who says that BASF has a prototype car with a gas tank that is filled with a MOF 177 running on methane. So just to connect to the previous comment.
Which is interesting because MOF 177 isn't one of the most stable MOFs. So it'll be interesting to see how that works over time.
The last question for the moment comes from Samya Mukherjee here. What is the target criteria for hydrogen storage by physisorbents that is provided by DOE guidelines?
I showed you the table a little earlier, and with the guidelines in them. So they look at both volumetric uptake and gravimetric uptake.
And they seem to have relaxed it as well.
Yes.
Yeah, and his follow-up question is this because there aren't enough MOFs that can actually reach that, or does that relaxation come from somewhere else?
I have a feeling the relaxation comes from just pure science, in that if you do a back of the envelope calculation, you would never be able to get to the specifications they initially had. So that's why I think they relaxed them.
Good. I think we are good to move on, Philip, please.
Okay, great. So the last part of the talk, what I'd like to talk about is a few applications. So we've just heard about methane and MOF 177 from BASF. So Cami Putti is going to talk to us next week or the week after about upscaling and problems towards upscale. I just want to highlight three features. So in terms of synthesis and shaping, we have to worry about reproducibility. Look at the synthesis to make sure that it's non-toxic or at least environmentally friendly to a certain extent. I mentioned activation, and we've seen with some materials activation can be a problem. We've quickly gone over cost as well. When we move towards applications, the one thing that we have to worry about is stability. As we come down to performance here, I've talked about imagining that we have to use an adsorbent for 5 to 10 years, for example. So stability could be along concerning storage with respect to humidity, for example. We saw this for MOF 5. And then stability during the use. So are the materials going to be stable to contaminants? Sometimes we'll have SOx or NOx. Are the materials stable to temperature? Temperature and contaminant sometimes is one thing. Once we have the materials in some sort of form, are they stable to pressure? And if we use, for example, a fluidized system, are the materials stable to attrition? And I'd point you to this this work from David Ferran in Cambridge, who has looked at shaping some MOFs, and actually found that the capacity is increased with the shaping that they've used. So of course, one way forward is to look at the work on artificial aging, and these are very important before moving forward. And then finally, in terms of performance, look at the performance under real conditions and with real contaminants, and I look to performance over time, as I said, talking about using materials over many years. So there are a whole series of groups and companies looking at upscaling MOFs or selling MOFs, and I'm sure that these are people to talk to about these problems here. So, as I said earlier, when I'm talking about research, what sort of gases should we look at? If we do the same thing here in terms of applications, what applications should we look at? So this is a very nice paper by David Scholl and Ryan Lively, who discuss the use of energy for separations and how it's a huge amount of energy. Almost half of industrial energy is used for the separation process. And using nanoporous materials could be attractive. So in the work by David and Ryan, they put forward the use of membranes, but as almost athermal separation, adsorption could also be one of interest. And they came out in their papers called 7 Separations to Change the World. And these are the 7 separations. And in terms of what I'm going to talk about in the next few minutes, so we've already talked about research of alkanes and alkenes. I'm going to show you 1 or 2 applications concerning greenhouse gases from dilute emissions. And I'll show you an application, one group, looking at the recovery of lithium, for example, from brine, so trace contaminants from water. So maybe the first if I'm not mistaken, one of the first commercial applications of MOFs was actually none of the ones I've just cited. So this is Trupric, a company that liberates this molecule here, methycyclopropene, so 1-MPC. So this is the molecule here, and it's something that is applied to fruits to slow down the ripening. So this is here we have some kiwi fruits that have been treated either without any treatment or treated with this molecule. You can see that these fruits are far fresher than these ones. So there's been there's a patent from Dr. Nazir Mir using this molecule in a metal organic framework. So if you go to this patent and try and go through and work out what is the actual MOF used, it's not easy to see, but I'm guessing that it's this material, so an aluminium fumarate type MOF. It's one which has quite small pores. Aluminium is quite a cheap metal, and the fumarate linker is also quite cheap. And what we know is this material is made by a Northern Irish company known as MOF Technologies. And I'm guessing it's being synthesized using liquid-assisted grinding. So the interest here is that the material has been upscaled to quite a large extent. The second application that we've heard about recently using MOFs is that's come out of Newmat Technologies. And many of you may know Omar Farha, who is here. And he's set up a company with this young man, Benjamin Hernandez, and they've partnered with Linde to put MOFs inside this tank for the subatmospheric storage and transport of some of these quite nasty gases which are used in the electronics industry. The interest here is that it's the storage is subatmospheric. So if there's a leak here, there will be a leak, hopefully, and at least initially, the leak will come into these bottles rather than coming out. Again, if you look around some of the literature, it's not easy to know what MOFs are inside. What I have seen is it may use a combination of two different MOFs. And looking at the work, or at least looking at the structures we have here, this structure looks very much like NU1000s. So it may not be the MOF in there, but it's I'm guessing at least one of the materials made in Northwest. Interestingly, there's been this work and publication, slightly controversial because the thermodynamics are maybe not as simple as we're seeing here. But so this company, water harvesting company, has been set up for the recovery of water under desert conditions. So if we need water from in the desert, then maybe it's possible to recover the water from quite arid air, and then once it's recovered in the material, use mild heating to recover the water, condensed water. So the idea is to make drinking water using only solar panels as energy in quite dry areas. So this is the setup that they have at the moment, or at least we can see on the internet. And they've just said that they've been able to harvest a few liters in over 24 hours. Again, the metal organic framework, if we look to the patents, or to look at some of their publications, we can see that again, this aluminium fumarate seems to be one of the materials they've been looking at. And this MOF 303, or this material here, is a second MOF that they've been looking at. And here they've compared the productivity here in blue with respect to the efficiency here, either under low flows or high flows. And we can see that the efficiency here for this material here, so the MOF 303, so this material here, under high flows seems to be the best. Moving away from gases and vapors, this is the use of MOFs for lithium recovery from quite dilute sources. So this the company's name here is EnergyX, and what what they're planning to do, or what they are doing, is using a mixed matrix membrane, using a UAO66 type material. So if you look at their publications, or look at the publications related to this work, they've taken this UAO66 and they've looked at different functions. Okay. You can see up here the sort of concentrations we're looking at, whether it's lithium from the ocean or from underground or geothermal areas. The concentrations are actually quite small. So this is what Lithium X claim, and they have a partnership with MOFs for the UAO66 material. So if you look at one of their recent publications, what they've tried to do is actually engineer the membrane itself. So here we have a PET membrane. They've put in sort of like bullet-shaped holes, and the idea is to grow the UAO66 material inside these pores or holes. And what they say is that they have a sieving by window. So this is the triangle window of the UAO66. We have here a dicarboxylate linker. And they say that there's stronger binding with 2+ ions, so for example, calcium and magnesium, and less so with these ions here. And they say that they can. This is one way to recover lithium. Finally, we heard from so the first talk in this series was talking about direct air capture, and Marco Mazzotti gave a very good talk on this. Moving away from some of maybe the bigger groups, the larger groups working on direct air capture, MOFs have been used, and this is work coming out of CSIRO in Melbourne and Monash University, and they have this this thing here, which and their process they call Athena, and so with this process here produces MOFs. And so it produces CO2 at around 2 tons per year. And here we have the power requirement. So you can see the footprint here of the unit is actually quite small. They have a high surface area MOF in the tanks, in the separation units here. And from what we can understand is not only the MOF, but also the gas solid contactor is a key element. So this is technology for direct air capture under a smaller scale than we would expect, or other people have been working on, but still quite an interesting niche for MOFs. So none of the separations or the storage that we've seen so far is we could say a large scale in terms of bulk separations. So to finally look at this, to one of the groups that are, or one of the companies that are looking at bulk separations is Fonte, formerly known as Inventis. And what they have is basically a setup in which they have quite a specific cycle, adsorption, release, sort of regeneration and cooling cycle. And this cycle is carried out in this rotary adsorption machine here. So this is a mock-up or a design of what they hope to be their largest machine, so around 15 meters in diameter. But they have rotary machines at smaller size. And what is interesting is that the whole cycle here is carried out in about 1 minute. So very fast, it's a fast temperature swing cycle. So they can do this because they have quite a short contactor, quite a short bed here. And inside they have a laminated structured contactor. So this is a laminate here. And on these laminates, they have different types of materials. And in their recent work, they've looked at one of this material here, known as CALF20, so initially prepared by George Shimizu. And they have an exclusive license to look at this material here on this laminated contactor. So the work that they're carrying out, or hope to be carrying out in the near future, is in this project known as CO2 MENS, looking at a cement plant and looking at the flue gas from a cement plant. Total, a partner in this project, along with Lafarge Holcim, and they're testing this rotary adsorption machine. So not this one, but this one here, which is what they call the Svanti 200. So I'm guessing around 200, maybe 2 meters in size. And the idea is to capture around 1,000 kilograms of CO2 per day. using this cycle here, so what they call the Veloxotherm cycle. What is of interest here is they're using real conditions with real contaminants, notably oxygen, water, and NOx, as well as particulates. So quite a challenging separation for CO2 for cement. We'll know more about the results in about a year, hopefully. So what can we see in terms of trends, and take this with a margin of error, because we don't know with all of these applications what are the actual MOFs inside. But from what we can see is that most of the things that we've seen are quite small pore MOFs. The MOFs that we have seen are all very stable to water and fairly inexpensive. The other thing that's quite interesting is to know that these first two applications that we've seen that seem to be commercial are not the ones that have been studied to a large extent in the academic field. The other thing is at the moment there's no bulk separation yet, but maybe this work moving forward with Svante could give us an idea of where MOFs could be used in bulk separations. So with that, how can we link the use of MOFs in research with ways forward in terms of novel applications? So here are some ideas. So I've already talked about flexibility. I'm not going to go back onto this. I did talk about right at the very start the problem of finding the right MOF for the right application. So one way forward is to use design, computer-aided design. So this is one way forward. The other way forward is taking the idea of the process and screening MOFs for a process, and this is what Arvind is going to talk about. And the third thing is lowering the regeneration energy. Now, one of the big things that we see in terms of separations anyway is this regeneration energy, and there are several ideas around to use magnetic induction. So this is what we're seeing here with different magnetic fields. We can go from our CO2 isotherm here and decrease the uptake with a magnetic field. Similar thing with light induction. So we're seeing here light swings. Okay, and of course microwaves could also be used to help desorption. So with that, just like to summarize, we've seen what MOFs are. We've seen some lab scale research, some very interesting lab scale research. We've seen the need for complementary understanding. So for example, where are the molecules sitting when they come into these cages? And I've gone through several applications here. I've not talked about databases as such or screening or more about this complementary understanding. And I've not talked about examples from other fields, for example, health or environmental sectors. I would point you to these books here. So there are several books around dealing with metal organic frameworks. And many of them have chapters devoted to different types of applications, whether these being catalysis, separation, storage, or whatever. So thank you for your attention. Stay safe. And I'll leave you with this slide just to give you an idea of all the different webinars that are in this series. So I would encourage you to move back and look at the first ones that are already on YouTube and look forward to the ones that are coming up. So thank you very much.
Excellent. Thank you very much, Philip. So again, I encourage our participants to post their questions. We already have a couple. So one comes from Angel Hojati. So for CO2 adsorption, is the mechanism chemisorption or physisorption?
So in the applications, we don't know an awful lot. I am guessing that it's physisorption, which could be surprising because many of the applications, for example, in direct air capture, if we look at some of the other groups, not the one from Monash, but the other groups, are using amine functionalized silicas or polystyrene or other resins. So many of the other groups are looking at amine functionalized materials. Whereas if we look at CAF20, for example, there are no functions on that. So I'm guessing it's a physisorption type mechanism.
So the next question comes from Malgorzata Kowalczyk. Are there any study of MOFs towards stability against regeneration, for example, steam or sodium hydroxide? Yes,
and this is done at the development stage. So I showed you the initial publication by Lowe in JACS 2009. But what I do know is that as you move forward, a lot of these steam regeneration testing is done. We'd have to look to the publication literature, but I know many groups are doing this, but I don't know whether they publish their results.
Excellent. The next question comes from Guoping Hu, and this is about the Svante process, I assume. Is the heating source for this process waste heat, or is it steam? And yeah, I think it's steam.
It's low-grade steam, and this is what we can see on their site, on the website anyway.
Yeah. So, and his follow-up question is, can you comment on potential heating sources if the MOF is water sensitive? Have there been studies also with waste heat in a way?
Not that I'm aware of, but so waste heat in terms of waste heat and stability, for example?
Yep.
Not that I know of, not that I'm aware of, at least in the open literature. And also, when we're looking at stability, for example, MOF stability, it's worth looking to the literature and some of the computational calculations. So this gives us an idea of what MOFs are stable.
Excellent. So the next question comes from Soumya Mukherjee. What are the steps for translating MOFs that show capability for binary ternary separations from lab to a process?
So
to industrial scale process.
Yeah. So quite often in the lab, we're going to be working on small scale materials, maybe powdered materials, or at least if they are shaped, they're shaped quite crudely. So the first step is to go back to the people looking at the synthesis to make sure that the synthesis is upscaled, it's reproducible. Next huge problem, and it's not one that people talk about a lot, is the shaping. Because this has a strong effect on the interaction of whatever gas and the active sites. So shaping is a huge problem. It's often a secret. There's a lot of secrets behind this shaping process. But again, coming back to our last example, the Svante process, they show that they're shaped on these laminates, which is quite interesting. We also know that, for example, there are people looking at tubes in which the material is on the outside of these tubes, and water is flows in the center of these tubes. So the shaping is a huge problem, and often, as I said, which is often kept secret. And then, of course, demonstration or lab scale pilots. So lab scale pilot is one thing, and then you move up from the lab scale pilot to sort of like an industrial pilot. An industrial pilot, for example, can be with real gases, and that then becomes, we have the big problem. But I think once we get to the industrial pilot, if there are no problems at that stage, then moving forward is a little less of a problem. A lot of the problems will happen from upscale to lab. I'm going to say lab industrial pilot scale, and that's where the problems arise.
Excellent. So I have a comment on YouTube from Omid Nick, who is the director of materials from Svante. It's interesting the kind of comments that you can get through this webinar. So he confirms that on Calf 20, CO2 is a physisorption mechanism. So yeah, that's just going back.
Thank you for the precision. I don't know whether I was allowed to.
Yeah, so I have it on record here. So, so the next question comes from Marco today. So regarding non-conventional regeneration approaches that you had mentioned at the end, can the limited penetration depth of light or microwaves through this matter can be a limit? Yes. And are these scalable in a way? Yeah.
So that is one of the problems. Is the penetration of some of these energy sources, and yes, penetration is a problem. Which is why magnetic heating. So imagine you have a MOF which is a magnetic MOF, a stable magnetic MOF. Magnetic heating may be of interest. Because it's heating directly at the metal centers. No huge problem in terms of penetration there. But yes, microwaves and light are two areas where scalability could be a problem. So if you want to go to much more larger scale applications, it could be a problem. So you'd have to be quite clever in looking at applications maybe on a smaller scale, maybe sensors, for example. That could be one way forward.
or even shaping would be another major way as well. Yeah. So the next question is, it's a very broad question, so you can answer to whatever extent that you think is appropriate. This comes from Masa Lole. So what are the most common methods of synthesis, MOF synthesis for industrial applications?
Ooh. It's not one that maybe I can answer because I'm not a specialist in the synthesis. I'm guessing most of the synthesis is sort of like liquid phase, solvable thermal type syntheses, because they're the easiest to adapt, easiest to do. We've seen that MOF technologies, they work a lot on this liquid assisted grinding. So basically this is one great big screw. Put in the materials at the start, you let them grind together, and they have the MOF material coming out at the end of the screw. So I'm going to say solvable thermal synthesis, liquid assisted grinding for MOF technologies. And in terms of MOF synthesis, there are patents from the CSIRO in Australia, in which they use I suppose microfluidics. So the reactor materials come out at the start, and then use microfluidics through small tubes and have the material come out at the end. So I think I've just seen one of the patents come out recently on that.
Yep. Excellent. I think that kind of brings us to the end. Guoping Hu has a question, but I think you kind of answered that earlier. So I would request you to just stop sharing the screen.
Okay, how to do that?
Just have a couple of announcements.
I have to go back down here. Give me just 2 seconds. Unless you can do that for me.
I can do that for you. Yep, I think it's good. So just a quick announcement. So same time tomorrow, we'll have Matthias Thomas talking about characterization of porous materials. As you know, Professor Thomas is one of the well-renowned people in the characterization of porous solids. So please do join us. Later on, we also have other talks that are coming up. Next week, we'll have Farouk and Nick Wilkins talk about breakthrough, how to set up a breakthrough and how to analyze it. That's mostly targeted for graduate students and early researchers who want to get this started. It's a technique that is so commonly used, but also not thoroughly used. On the 12th, we have Kutsumi Kaneko representing from the Asian contingent for this IAS webinar series. And we also have other talks scheduled. So I thank you for your attendance, and stay safe. And we'll have this webinar uploaded on YouTube as soon as we can. Thank you and take care. Bye-bye.